So at last, there's a minor talks on this chapter. So firstly, why this short? It is because this chapter contains nearly no content, just one theorem and one corollary, because I want to throw all these number theory stuff to the fifth chapter, so that you could have a more comprehensive point of view. I'm talking about number theory. And the second thing is there's some details that I wrote down but I didn't talk about this, so it may be less detailed than you think. And secondly, I would like to talk about the proof of the Steinhaus theorem in Rn. Now, in the previous proof, we actually showed that the intersection between E and x plus E is actually non-empty, but we could in fact show that it is a set with positive measure. It is a set of positive measure. Now, the proof of the theorem in Rn actually made use of this. The sketch of the proof is actually like this. So we define a function phi x, which is the big measure of a set at its translations intersection, and yes, it has an integral representation which is like this. It has an integral representation, and hence it is not just continuous, it is absolutely continuous. So, and you know that the phi of 0 is actually the Lebesgue measure of E, which is positive, and of course on the neighborhood, by continuity, it is positive. And then you know that when x is smaller than some delta, this thing is greater than 0, and this thing is greater than 0 simply means this is non-empty. Then there exists x0. Just repeat the argument. Now you could directly use the integral representation and the absolute continuity of the integral, and you could actually derive this from scratch. It's primary school mathematics. Just start from 2 cubes and calculate their difference. And that's all I want to talk about.